Hello everyone, we are Team MetaMinds. We present our final year project, Metacognition Aware Personalized Feedback for Algorithm Design Problem Solutions. Let's start with the problem space. Most existing intelligent tutoring systems in programming domain focus primarily on introductory level tasks. They use large language models to suggest corrections or give generic hints for codes. However, these systems often fail to personalize feedback based on how individual students learn or think. More importantly, they don't consider metacognition, which is a student's awareness of their own learning strategies. And lastly, these systems are usually not optimized for competitive level programming problems. So we asked ourselves, can we build a model that generates feedback tailored to both the student's code and how they think? Which we defined our research objectives as create a dataset that includes algorithm problems, student submissions, metacognitive measurements, and feedback, and develop a metacognition aware model called MetaHelp to generate personalized feedback. Then deploy this system as a Moodle plugin to make it usable in real-world educational settings. To overview our methodology and start the solution development, we started it by developing the MetaFeedback Ad dataset. As we can see here, we developed a metacognition measuring questionnaire, and we developed the metacognitive feedback Ad dataset as overviewed in here. First, we adapted the questionnaire from Fernando and Vijayaratna for the mathematics domain into the algorithm design domain, and we cross-validated it with the PCDIT framework and content validated with expert support. Expert provided an agreement percentage where 14 questions out of 16 have received the expert agreement above 75%. This questionnaire was used to measure the metacognition levels of the students. Then, MetaFeedback Ad dataset had two parts, MetaFeedback Ad Introductory and MetaFeedback Ad Competitive. This contains the introductory level dataset, programming submissions from first year students at the University of Moratuwa. We collected data from two assessments, PP1 and PP2, totaling into 16,803 instances, and students responded to a 16-question metacognitive self-assessment to get their metacognitive profiles separately, and we merged code and metacognitive data using student IDs. For the competitive level dataset, this was created through a hackathon involving second and final year students. Students solved 6 competitive tasks, 2 introductory, 2 easy, and 2 medium tasks. We gathered 372 instances, including code, difficulty level, and the student's self-rated programming levels. The data fields included problem, student code, expected code, difficulty level, which importantly included in the competitive level dataset, the metacognitive vector, and the metacognitive feedback. For the dataset preprocessing phase, here we merged the dataset, and as the clean process 1, we removed the null values, duplicate values, and the erroneous values, and that clean dataset was moved on to the clean process 2, where first we annotated the dataset with the ground truth with the chain of thought prompting using the GPT 4.0 mini model, and we evaluated the generated text quality at this clean process 2, and we developed it into the MetaFeedback Ad introductory dataset. To describe the cleaning process 2, here we generated 2 feedbacks from the Mistral large lattice model and the GPT 4.0 mini model, and we obtained the embeddings respectively from the Mistral feedback and the GPT feedback using the SBERT model, and we calculated the cosine similarity score where we used the intuition of if the score is greater than a calculated threshold, it will be added to the dataset, and if not, they will be regenerated. And this developed introductory level dataset was expert validated after sampling, and with the support of one expert in education and programming domain, Professor Kenny Liu from Singapore University of Technology and Design. Here, we offer 2 training test splitting strategies for robust evaluation. DMP split means distinct metacognitive profiles. Train and test sets have non-overlapping student profiles and programming problems. SMP, similar metacognitive profiles, ensures equal metacognitive trait distribution across splits. This helps benchmark generalization performance under realistic and challenging conditions. Moving on into our MetaHelp framework, the novel and the innovative part of our project, given the question, the student solution, the correct solution. MetaHelp builds a context embedding using the decoder-only LLM. Parallelly, the students' answers to the 16 metacognition questions are encoded into a metacognitive profile, as we can see here, using the LoRa adapters and by scaling and by the element-wise multiplication and concatenating sequentially according to weighted embeddings. And after obtaining this metacognitive embedding and both the context embedding, which includes the programming questions, runs code, and expected code, we obtain the cross attention between them and we pass them as an input to the decoder only model, which we train using LoRa adapters, and it will generate the metacognitive feedback. We use cross-attention to align contextual code features with the relevant metacognitive behaviors of the students. The final merge representation helps the model focus on both what the student did and how they think. So, let's move on to the experimental study. So the experimental setup, we used QuentCoder 2.5, 1.5 billion instruct for feedback generation, which is the baseline model, which is well suited for programming contexts. As for the training setup, we used LoRa rank as 16, alpha value as 32 for best performance, input length truncated to 1536 tokens, trained for 3 epochs using AdamW optimizer. Only LoRa weights were trained, keeping the base model frozen for efficiency. For the experimental results, evaluation matrix from NLG domain were used to evaluate the feedback: SBERT, ROC, Meteor, and Comet. Here, according to the given ablation study under DMP split, ablation study under SMP split, MetaHelp outperformed all baselines including prompt-only models and fine-tuned LLMs without metacognitive inputs. Even compared to Mistral and CodeLlama, MetaHelp achieved superior scores across all matrices. So, generalization evaluation of MetaHelp. Despite being trained on introductory data, MetaHelp generalized well to competitive problems and new student profiles also. In the user study with 21 final year students, MetaHelp received the highest feedback scores for clarity, helpfulness, and alignment. So as a final stage of our final year project, using MetaHelp, to bring MetaHelp into real classrooms, we built a Moodle plugin called CodeRunner Meta. It integrates MetaHelp via API, which automatically collects metacognitive profiles using the Moodle-based questionnaire, and it provides metacognitive feedback beyond test case results. This plugin can be installed directly from the Moodle admin panel, making deployment simple for instructors. Here's a sample Moodle plugin generated output, and here are some examples for low metacognition profile, where feedback emphasizes code clarity, input handling, and step-by-step debugging, and high metacognition profile, where feedback suggests optimization, explicit logic, and edge case handling. This each measure is tailored to the student's thought process, not just to their code output, as we can see. So, as for future improvements, add more competitive level questions, extend support to multiple programming languages beyond Python, explore large language models with cross-attention like MetaHelp, more enhanced large language models, more capable ones, enable dynamic metacognitive profiling that evolves through usage. To conclude, we introduced MetaHelp, a system that generates personalized, metacognitively aligned feedback for algorithm design problems. So our meta-feedback add dataset and feedback generation process were expert validated and empirically tested, where results show that integrating student metacognition into feedback significantly improves learning support. Let's view a simple demonstration. That was a simple demonstration where we integrated MetaHelp into the custom developed existing CodeRunner in Moodle, which we named CodeRunner Meta. So, thank you for watching.